big radii, that people were able to see that the rotation was too fast to be explained by just the visible mass in galaxies. So you need an extra large, spherically symmetric, fluffy component of galaxies with maybe 5 or 10 times as much matter as was observed to explain these rotation curves. So more evidence has come along in the meanwhile. The oscillations of the CMB require a larger restorative force from gravity than would normally be seen from just from looking from the baryons available. And there are measurements such as gravitational lensing that point to a large invisible components of matter that are lensing galaxies that are in the far distance, or lensing the light of galaxies in the far distance as it passes through clusters of galaxies. And I just want to point out that this image is not the bullet cluster. Usually the bullet cluster is used ad nauseum in these presentations, but there have been other observations in addition to the bullet clusters that corroborate sort of this view that dark matter is necessary. So what do we know about dark matter? Well, from gravity, we know that it has to have a very small self-interaction cross-section. This means that you don't want dark matter to efficiently radiate its energy away and collapse to form disks like galaxies. You want it to stay large and fluffy. You need these large spherical halos to explain the rotation curves. CMB and lensing tell us that, and also galaxy physics tell us that there's very small interaction with the standard model. And other observations tell us that it has to be massive enough to have been non-relativistic, or only mildly relativistic at the time of decoupling, so that the galaxies, the structures that we see today, would be able to properly collapse. So if the dark matter was too hot, too fast, then these structures would have just streamed away rather than collapsing. And we know the abundance of dark matter relative to the abundance of the standard model in terms of energy densities is about a factor of 5. And this in itself is quite interesting, because to get abundances of the same order of magnitude, you can assume that dark matter was in thermal equilibrium. The volume of the microphone. Can you hear me, actually? Can Ahus hear me? You can hear, okay. Turn up your volume, I don't know. Okay, good. So the freeze-out abundance of dark matter depends on the self-annihilation cross-section. So it's this equilibrium, equilibrium between the rate of production of dark matter and the rate of expansion of the universe. And when these two rates are equal, then the abundance of dark matter freezes out. And it turns out that to get the correct thermal relic abundance, to get that factor of 5 that we saw earlier, we need a thermal annihilation cross-section that's order 3 by 10 to the minus 26 centimeters cubed per second, which is about the same cross-section as processes that interact via the electroweak force. So this prompts speculation that dark matter could be some weakly interacting massive particle, weakly in the sense of electroweak. So whatever the channel, a thermal origin like this implies that interactions between WIMPs, so annihilations of WIMPs into standard model particles, are still ongoing and would have been ongoing from decoupling all the way to recombination all the way to the present day. And a good question then to ask is, well, can we see such a signature? Well, what do we know about the particle properties? So this was all, remember, this was all from, well, mostly from gravity, from arguments due to gravity. Very briefly, there are direct detection experiments that have looked for nuclear recoils. Collider searches, which are very difficult, look for production, sort of the opposite of what I was talking about just now. So production of dark matter from annihilation of standard model particles in colliders. And many indirect searches, like looking for annihilation signals, gamma rays, for instance, in dwarf galaxies in the galactic center. So there have been, recently, there's been a lot of hype over this Fermi line, the 130 GeV Fermi line, as well as diffuse gamma rays from, well, dark matter annihilating in the whole universe, neutrinos from capture and annihilation in the sun, heating of the intergalactic medium, which I'll actually get back to later, excess antimatters such as positrons, antideutrons, etc., and traces on the cosmic microwave background. So this is what the rest of the talk is going to be focused on. So the CMB, as we all should know, is this uniform black body surface that we observe in the sky that corresponds to, well, it was emitted at a temperature of about 3000 Kelvin when photons and baryons decoupled as the universe cooled at a redshift of about 1100. And the temperature today is about 2.7 Kelvin. The anisotropies are really what we're interested in right now. So how do these occur in, well, briefly in 2 slides. So after the end of inflation, different regions of the universe slowly began to causally reconnect as the expansion of the universe was now not faster than, was now not driving perturbations away from each other at faster than beyond the horizon. So as different regions entered into causal contact, the smaller perturbations enter into causal contact first because of they're on small scales. These regions start to causally reconnect, and any overdensity or underdensity that was produced during inflation would seed oscillations in this fluid of photons, baryons, and dark matter that the universe is left with after inflation. So the power spectrum of these oscillations comes from the power spectrum that's seeded by inflation, or whatever your favorite inflation alternative is. Well, these oscillations are maintained by gravity, so the collapsing overdense regions, and as well as pressure from this baryonic fluid, or photon baryon fluid, rather. So at high temperatures, these photons and baryons are tightly coupled, so the photons and electrons are and protons are scattering off of each other like mad. But as the universe continues to expand, this fluid cools, and eventually the hydrogen atoms recombine. And once the temperature reaches something like 1/10 of the ionization potential for hydrogen, then the photons in this fluid can't excite hydrogen atoms anymore, and the medium essentially becomes transparent. So what you see when the photons then just stream away is a snapshot of this last scattering surface, which is the last time that photons could escape without scattering with hydrogen or with free ions. So what explains then this map of the sky that we see when we look at these CMB anisotropy maps? Well, the hot overdense regions from the CMB emit higher energy photons, but as they escape the gravitational potential of these overdensities, they are redshifted. They're actually redshifted more than the temperature fluctuation would have given you in terms of a redshift or a blue shift. So this is called the Sachs-Wolf escape. Furthermore, there's the relative motion of this oscillating fluid, which redshifts or blue shifts the photons. This is just, well, this is the Doppler effect. And there's an integrated Sachs-Wolf effect, which is the effect of photons passing through gravitational potentials that are either shrinking or growing with time as they travel from the CMB, or from the surface of last scattering to our position. So the map that you see in the sky then is going to be a sum of all of these components. The Sachs-Wolf effect, the Doppler effect, which is out of phase. Think of a harmonic oscillator and the velocity with respect to the amplitude fields. And then the integrated Sachs-Wolf effect. So the point is that these CMB photons after this have a long way to travel from last scattering, 13 billion light years. So if there's an extra energy source between the production, between the surface of last scattering and where we observe them today, then this might rescatter these photons, and this might affect what we see in the cosmic microwave background. And the question is, well, can we detect this? So, okay, so how is energy deposited into the intergalactic medium from this annihilating dark matter? Well, the annihilation rate, so the rate of injected energy, is just proportional to this cross-section, this annihilation cross-section, times the number density squared. And so the injected energy is this rate times the mass of each particle, the mass being the amount of mass energy that's available to be injected into the medium. The number density of matter goes as the scale factor to the -3, so to the 3. So this goes as 1 plus z. So each factor of n goes as 1 plus z cubed, where 1 plus z is the redshift. So in the end, you get an amount of injected energy that's proportional to 1 plus z to the 6th. And you also notice that this goes as 1 over the mass, which explains these exclusion plots that you'll see here and you've seen before, where sigma v, the constraints on sigma v go as the mass. So the deposited energy, so this was the injected energy from annihilation. The deposited energy is a different story. And what I mean by deposited energy is the amount of energy that's released that actually gets injected into the intergalactic medium to either heat it or to ionize the medium. So the final state particles that are so-called invisible, or that don't interact electromagnetically, don't heat the intergalactic medium. So neutrinos from this type of annihilation will just stream away until the present and have no effect, direct or indirect, on the CMB. After that, the deposition efficiency is going to depend on the transparency of the intergalactic medium to each of the daughter particles of this annihilation at each redshift and also at each energy of these daughter particles. And finally, as I said, heating and ionization are electromagnetic processes, which means that the final states that really matter are electrons, positrons, and photons. So if you have, say, an annihilation into muons, then what you'll really be looking at is the effect of the electrons and photons that result as a final state from these interactions. So how do you compute this energy deposition into the intergalactic medium in a practical way? So you start with some dark matter annihilation event at some early time, for instance. You calculate the final state spectrum for each of these daughter particles. Then you calculate the energy loss to the various processes that have to do with, well, that will cause your electrons and photons to lose energy in the intergalactic medium. So Compton scattering, Coulomb scattering, ionization, pair production for each of these species. Then you compute the amount of energy you lose to all of this and the amount of energy you lose to redshift. Step forward to the next redshift. Step forward to the next bin in redshift in your numerical calculation, and then repeat. And so you need to do this for each redshift of injection and each redshift of absorption. And so what you wind up with is some transfer matrix, which we'll call Ti, which maps the fraction, the total energy injected at a redshift Z prime to a total energy deposited into the IGM at a redshift Z for a given initial energy EI. So in that way, from this transfer function, and this has been calculated and tabulated very nicely by Tracy Slatcher last year, we can rewrite our energy injection exactly in the same way as before, but with some function f. F of redshift and dark matter mass that parametrizes this energy deposition efficiency. So this energy deposition efficiency, don't get scared of this expression, is so the numerator here is what gives you your properly computed energy deposition, and the denominator here is this is nothing but a normalization, so that we can use this this form here as a question.
So why is the 1 plus z?
Yeah.
1 plus z is not is the z, right?
Why? So your question is, why is the 1 plus z
The 6 is not equal.
to the 6? Right. So we've pulled out a 1 plus z to the question was, why is the 1 plus z to the 6 here, right? Not in the integral. And the answer is, well, it's actually down here. So we've pulled it out and put it back in again so that we could re-express it in the same way as 1. But this 1 plus z to the 6 doesn't, I mean, it cancels here, so it doesn't really have a physical meaning. It's just nice to be able to write it like that. So I mean, this is just explaining what these various parts of this would be. So your particle physics, so the spectrum of the final state particles after dark matter annihilation is in blue here. And these factors of 1 plus z come from your redshifts and come from your, well, the appropriate redshifting of the density of matter, as well as the conversion from an energy injection rate to an energy per unit time to a rate per unit redshift. And this function Ti is the thing that encodes all of the physics of the intergalactic medium. And so you integrate over all redshifts of injection, dz prime, and over all energies to get the efficiency of deposited energy at a redshift z, considering this expression. So, like I've said, this energy deposition efficiency depends on energy and also depends on redshift. So if you take one slice, this is at a redshift of 100, and this is the inverse of the cooling time, the y-axis here, which you can just see as the energy deposition efficiency. So at very high energies, you can see this is for a photon that's traveling through the intergalactic medium. So if the photon has very high energies, then it deposits its energy extremely efficiently by pair creation. At low energies, meanwhile, it's extremely efficient at depositing its energy by ionization. And just above that, there's this hump that's due to Compton scattering. But you can see here between, this is 10 to the 8 and 10 to the 10 electron volts, there's a region in which deposition is relatively inefficient. So this means that a photon that's emitted at this energy in this redshift has a very good chance of just freely streaming in the universe and depositing its energy. So it redshifts as it evolves in time, and deposits its energy in this Compton bump at much later times. So what this looks like, so you can't really read the axes very well, but this is the x-axis is the redshift z, and the y-axis is now the mass of the dark matter. And what you're seeing here is a plot of the efficiency. So just this function f of z and m of deposition from dark matter annihilating to 2 electrons. So you can see that at very high energies and very low redshifts, this is fairly, very high masses and very low redshifts, this is fairly inefficient. But you get into this region here, for example, which is a mass of around 100 MeV, where dark matter is actually emitting photons and electrons somewhere in this region, and they're getting redshifted and pile up in the region of efficient Compton scattering. There's an analogous plot for electrons that can be done. And so these guys, what you wind up with is an efficiency that can be even larger than 1 at low redshifts for certain mass ranges. So obviously for other mass ranges, this is less than 1, say here, or down here again. So this efficiency really depends only on physics of the intergalactic medium. And once you've convolved that with the spectrum you expect from your dark matter annihilation, you get a picture of what your dark matter is actually doing to the intergalactic medium. So, well, what does this do now to CMB photons? So you have this deposited energy that we've just calculated now, and this can go either into heating or into ionization of the matter that's present in the universe. So these factors G just tell you the respective efficiencies for heating and with respect to ionization of the medium. And all these guys down here, so these are normalizations to the matter content. And this just comes from changing your rates per unit time to rates per unit redshift. So the dark matter annihilation rate, as we've seen, goes as 1 plus z to the 6th. And after that, once you include all the proper factors of the redshift here, and there's one hidden in the matter density here, then what you wind up with is a proportionality to 1 plus z to the 1/2. And this means that the efficiency of energy deposition, or the efficiency of heating and ionization, gets larger as you go to higher redshifts. So the early universe is really when you would expect to see a very large contribution from dark matter annihilation. And when I talk about the early universe, I mean redshifts from 1100 until now, so from the last scattering surface until the present day, which is when these CMB photons are propagating, so when we, the region where we expect to see any visible effects. So around a redshift of 1000 or 1100, what happens is that you have this increased ionization that's due to these terms here. And the effect of this is to delay recombination. So you have an extra source of energy that's ionizing the universe as it's trying to deionize, as it's trying to cool. And the effect of delaying recombination means that the last scattering surface actually looks large structures, so I can see cars and houses, but since the focal plane, well, this time it's in my retina, is larger, then I can't make out smaller correlations. I can't read the text on my screen, for instance. So this means that at higher multiples, the correlations will be smaller, and at lower multiples, they would stay pretty much the same. Interestingly, this is degenerate with a change in the scalar spectral index, because if you tilt the spectral index, then you also get a suppression at high multiples, for obvious reasons. And we'll see later that this can be disentangled by late time effects. So here's an illustration of what it looks like in practice. On the left-hand side, you have the ionization fraction, Xe, as a function of redshift. So normally the ionization fraction would decrease as the universe continues to expand and hit some floor around here. Whereas when you add dark matter, then it decreases, but it hits some floor that's a bit larger. So so you have those extra ions in the universe that the CMB photons can scatter on. So your surface of last scattering is not where you would expect it to be. And you can see on the right the effect on the CMB spectrum. So you can see at low multiples, there's not much of a difference. But in the blue dash curve is what happens when you add highly interacting dark matter. You see this suppression at high multiples corresponding to small scales in the sky. So what happens at late times now? And by late times, I mean, say, Z smaller than 40. Well, what happens is as you continue to ionize the intergalactic medium, you're increasing the chance that a CMB photon will rescatter at some point between the surface of quote last scattering and the present day. This increases the optical depth of the universe, And so this affects the reionization history, and it will actually change the polarization spectrum. So what happens at low redshift is that, again, you blur out correlations on small scales for the same reason as before. But also, you're going to increase polarization correlations on large scale. And this is because Thomson scattering can only rescatter photons that have a given polarization towards the observer, meaning that you'll get some correlation which has to do with the distance, some increased correlation which has to do with the distance from us to that surface of rescattering. And it's a bit like looking at the sky. The sky is effectively adding correlation to the polarization of the sunlight that wouldn't have been there if the light hadn't rescattered on the sky. So here's an illustration of what happens. Again, the temperature correlation on the left is the same plot that I showed before, whereas on the right you have the polarization correlation. So the thin dotted line here is what would happen with very little dark matter or no dark matter. And as you can see, there's this increase in correlation as I increase the interaction cross-section of dark matter, which means that I'm injecting energy at low redshifts, and so I'm rescattering photons at low redshift, and I'm increasing polarization correlations on small multipoles, i.e. on large scales. So there's another effect at late times that I haven't talked about yet, and this is the effect of halos. So the dark matter annihilation rate goes as the number of dark matter particles squared, n squared, and collapse and formation of halos, so clusters of galaxies and galaxies, has the effect of boosting the annihilation rate by a very large factor, because you're increasing the average value of n squared. So this, to compute this properly, you need to integrate over the density distribution of halos. So in red here, I have the distribution function of halos, which can be obtained just from n-body simulations. And on the right, you have the concentration, the extra concentration of each individual halo. And this comes from integrating over the radius of each halo, over the density squared of each halo for each given mass. And then I integrate over masses and over the distribution function of halos of mass m to get the average of n squared. Now, and so we use an NFW profile, which is a standard parametrization. And in practice, you need to use the results of an n-body simulation. So we've used the big Bolshoi, or the multi-dark simulation, which gives very nice pictures, such as the one on the right here. On the left, you can see the effect of this extra contribution to n squared. So this is the redshift on the x-axis, and the y-axis you can see is the efficiency of dark matter annihilation. So this is for different masses of dark matter, but that doesn't matter too much right now. So you can see that the efficiency decreases gently as redshift goes down from surface of last scattering to today. And then when halos start to contribute, there's this massive increase by several orders of magnitude in the efficiency of dark matter annihilation. And so this effect can be seen in the reionization history of the universe. So this is similar to a plot that I showed you before. So this is the ionization fraction, and plotted versus redshift. So high redshift is up here. The last scattering is 1,000 here. I'm really sorry about the resolution. And as the universe cools, normally you would expect that cyan line. So the ionization would go down, hit some floor, and then as the first stars begin to reionize the universe, you expect some very rapid increase in the ionization fraction of the intergalactic medium. However, with annihilating dark matter, you would reach some floor that is not the same as you would normally expect, and then halos would begin to produce extra heat around, or inject extra energy into the intergalactic medium around a redshift of 200 or so, which would sort of give you this two-step reionization. And actually, a lot of authors have tried to just obtain reionization of the universe just from halos, which is interesting in itself. We didn't do this in our work. We just considered this mixed model that looks like this. So by the way, these are two different values for the reionization redshift. But essentially, these, you can see these graphs as illustrating more or less the same thing. So we just considered this mixed scenario. So we also included the effect of reionization in our work. So our actual analysis now, now we get to the interesting stuff. We performed a Monte Carlo over these parameters, so the baryonic content of the universe, the cold dark matter content of the universe, the reionization redshift, the scalar spectral index, the amplitude of the primordial power spectrum, and the dark matter self-annihilation cross-section. So we performed one of these for each of a set, for each value of a set of dark matter masses, to extract the 95% confidence limit on how much annihilating dark matter can we actually allow and still be within bounds from various experiments. So to do this in practice, we used these codes CAM, CosmoRec, and CosmoMC for the Monte Carlo. So the analysis itself, we used the newly released 9-year WMAP data. This was released in December of 2012, as well as the South Pole Telescope December 2012 data release. We also used various BAO measurements and some stuff from HST to constrain H0. So we looked primarily at this dark matter to electron-positron annihilation scenario, and also the 2-muon scenario. One reason that this E plus E minus channel is interesting is that, well, it's going to be the most constrained, since all of the energy practically goes into heating the intergalactic medium. So you would expect bounds on other models to always fall above this particular channel. It's also interesting if if this is the kind of thing that you're interested in, explaining a few anomalies or so-called the integral 511 keV line from the galactic center, and even the diffuse radio emission that we see from Arcade, and that hasn't quite entirely been explained. A lot of authors, of course, have done this kind of work before. A lot of authors have looked at other channels. So we're sort of concentrating on more of a deep approach rather than a broad approach. But we certainly intend to keep going on this. So there are two further constraints in addition to the CMB that can be considered from annihilating dark matter in the intergalactic medium. One is the temperature of the IGM. So Lyman-alpha measurements have put the temperature between redshifts of 2 and 5 at around 10,000 degrees Kelvin, or at a maximum of 30,000 degrees Kelvin. So you can use this temperature measurement as an upper limit to how much energy the dark matter annihilation can be injecting into the IGM before you actually overheat it and before you produce too much heating with respect to what's actually measured. And a second constraint is the optical depth of the universe. So the Gunn-Peterson observations of Lyman-alpha absorption lines also give us very strict constraints on when reionization is expected to have occurred. So at Z greater than 6, they observe that these observations tell us that the universe is not yet fully ionized, and by a redshift of 5.5, this ionization is nearly complete. What's somewhat irritating is that this is in conflict with WMAP measurements of the reionization optical depth, which actually favor a much earlier reionization at a redshift of 10. So it's been suggested actually that annihilating dark matter could actually increase the optical depth of the universe for reasons that I explained earlier, which would bring WMAP and the Gunn-Peterson observations back into agreement. Unfortunately, will turn out to be excluded just by regular CMB observations. So here is, without further ado, a plot of our exclusions. So as you can see, this line here would have been the old bounds that have been computed by several authors using WMAP7 and SPT 2009 data. And so we've improved these bounds down to here. This is the electron-positron annihilation channel. We've improved these bounds by a factor of 3 or so by considering the WMAP9 data and the South Pole Telescope 2012 data. And you can see the difference between not using the efficiency factor that I told you about earlier, this f of z. That's the red line, and this somewhat difficult to see, sorry, green line is what happens when you do use it. So at high masses, the dark matter annihilation, or the deposition of energy by dark matter annihilation is somewhat less efficient, whereas as you get to low dark matter masses, then it becomes more efficient. And I should point out that the relic abundance cross-section, which is 3 by 10 to the minus 26 centimeters cubed per second, is here. So actually, if you want to produce your dark matter thermally in the just standard vanilla WIMP scenario, you're going to start to have problems starting around 30 GeV or so. I also illustrate the muon channel. So this is dark matter going to two muons in black. And of course, it stops at 106 MeV, which is the mass of the muon. So what are the results for the matter temperature? On the left, you can see for various masses, which are illustrated in the legend down here, the effect of increasing, the axis is not very easy to read. It's not very possible to read. The effect of increasing the annihilation cross-section on the temperature of the intergalactic medium. This is at redshift 3, I believe. So as you increase the mass, the temperature increases up until you hit this bound, which is this black line. But I want to draw your attention to these barely visible with this resolution brown points, which is where the exclusions are from our CMB bounds. In other words, increasing the annihilation cross-section would hit the temperature bounds were it not for these CMB bounds. And I'll show these on the same plot in a second. This might be a bit clearer. And the same thing for the optical depth. As you increase the dark matter annihilation cross-section, the optical depth starts to slowly and then extremely rapidly increase. But if your hope is to reconcile reionization at a redshift of 5.5, which is this figure, with the WMAP measurements of the optical depth, which is this cyan band, this is the 1 and 2 sigma contours. If your hope is to reconcile these two, well, it doesn't quite work, because you need an annihilation cross-section that is actually excluded by quite a lot by our CMB temperature and polarization measurements. This just shows what happens to the optical depth if you start out with a reionization redshift of 10 rather than 5.5 up here. So here are all of our plots, all of our results put together. So again, we've pushed the constraints down by a factor of approximately 3. And these temperature bounds lie, as compared with the CMB measurements now, these are not the best constraints. on annihilating dark matter. And Gunn-Peterson constraints, so assuming a reionization redshift of 5.5, I believe, give you these constraints. But these are much, much less constraining than our temperature and polarization, our CMB temperature and polarization measurements. So the salient points of these results, and I'm almost ready to let you go. We've improved by a factor of 3 the constraints on annihilating dark matter to electrons and positrons and to muons and well, mu plus, mu minus. We found that the matter temperature using a halo deposition model from the big Bolshoi / multi-dark simulations doesn't give bounds that are more constraining than what we already got from CMB temperature and polarization data. And this means that in the end, it's the early universe, it's annihilation in the early universe, at least for these channels, that dominate over late time effects in terms of constraining dark matter. And finally, we didn't manage to reconcile the Gunn-Peterson and the WMAP measurements by using energy injection from dark matter. So here are the conclusions, some of which are repetitions of what I just said. So I've told you a bit why dark matter is interesting and why it's worth looking at the CMB in order to constrain the dark matter annihilation cross-section. And so to do this, we've included a full time and redshift in energy-dependent deposition model. And we've included as well the effect of halos using state-of-the-art dark matter n-body simulations. So we've improved constraints, as I've just said, and so we've shown that the thermal abundance cross-section, to have the thermal abundance cross-section and the dark matter to electron-positron annihilation, you need a mass that's greater than 30 GeV, and for mu plus, mu minus, this is about 10 GeV. And finally, as many of you know, I'm sure, we have 1 week to go until the Planck data is released. So we're looking forward to see what they have in store for us. So thank you.
Okay, thank you very much. Are there questions? I don't see questions.
Questions?
Okay, can I ask a question myself?
No, of course.
So, I mean, this factor 3 improvement of the bound is, do you understand where it comes from? I mean, why do you expect such a big contribution just from going WMAP 7 to WMAP 9? So, do you understand what is the reason for this big improvement? Would you expect an improvement coming?
So we found that it's a combination of actually the new WMAP data as well as the new South Pole Telescope data that gives us this nice improvement. And as for Planck, we would expect, I mean, our best guess would be, and following some rough estimates that we made, some rough forecasts that we made, we would expect a factor of 5 or so improvement with respect to these bounds that we've computed with WMAP 9. Yeah.
Okay, thanks. So I see there are questions from Daisy. Okay, can you speak?
Hi, can you hear me?
Yes.
Okay, so I'm Carmelo. I have a couple of questions about, first of all, if you tried to use also ACT data together with SPT data.
We didn't try to use ACT data now.
Okay, and okay. Also, I want to ask you if you have tried to use a realistic model for the reionization history, and not just the step function that you showed us.
Yeah, so we didn't use anything. Well, we used a sort of a glorified step function, so a smoothed step function, because this is sort of the standard in Cosmo Ray.
So in principle, you are able to. I mean, if someone provide you a different reionization history with a certain function of redshift, in principle you should be able to understand how much these change your results.
Yeah, I think so. And I mean, you can sort of guess from looking at these plots of the reionization history that I showed way earlier. Are you asking whether the constraint will change, or?
Exactly. So, but suppose that the reionization is not so fast, but is a little bit smooth. So you could test the effect on the final constraints, right?
Yes.
Yes, because 1 month ago we had a meeting about this topic here in Hamburg with all the people more or less involved on these things. You know, the group of Silvia Galli, Fabio Iocco, and many of the people that you cited in your during your slides. And we all agree that the only missing piece to understand the uncertainties in this kind of calculation is to test a realistic reionization scenario. So since you show that you have more or less all the machinery ready, so it's just it will be a good thing is that in the near future you can also think about this possible result.
So I think you're right that would be very interesting. There's one comment that I would like to make, is that we included this effect of the halos, which you can see looks quite large in here, and you would have some, if you added some realistic reionization history, you would have maybe some variation on this theme. But the point was that the constraints on the dark matter annihilation cross-section weren't constrained that much, weren't changed that much by this increase in ionization at earlier times. And I agree that, yeah, this part of the curve would be quite interesting to look at, because I mean that would change the polarization data. Yeah.
I agree with you, but today we are at the point that we can do our constraints better than 10%. So it would be nice to see how much, even if everybody knows that that the effect should be negligible.
No, I absolutely agree. Yeah, it's worth doing. Yeah.
But it would be nice to know how much is negligible. So that's just an invitation for future application of your model.
Oh, thank you.
Okay, so there is a question from Sanjeev. Sanjeev?
Aaron, can you hear me?
I can hear you. Hi, Sanjeev.
Hi. So it was really a nice talk. If my understanding is correct, in the recent WMAP9 data and the SPT data, there are some conflict in the higher modes, basically, right? They don't agree.
That's the okay. Yeah, Olga is whispering to me right now. This is a conflict between SPT and ACT, actually, not
with WMAP9. Okay.
So yeah, yeah, keep going.
Yes. So suppose if we add the ACT also information here, okay. See, when these two data sets are not matching with each other, even in the standard scenario, you know, how would be difficult to include all the data set in this kind of analysis?
I'm afraid I'm not the person to ask that question to.
No, Sanjeev won't be very different.
So I have a guest.
Hi, Sanjeev. How are you? So it won't be very difficult. I mean, it's just to add in the analysis ACT, as Carmelo just asked, right? We didn't consider ACT the high multiple data. We consider only SPT high multiple data.
I think it's
We can add it, but I mean, ACT and SPT, they are inconsistent from the ACT collaboration, and you just add it to the WMAP 9 likelihood and the SPT likelihood in case you want to combine the three of them. But I mean, we didn't consider ACT data. This is a good question, and we will do it eventually to compare what are the constraints if we do ACT plus WMAP 9-year data rather than SPT plus WMAP 9-year data. Okay.
Okay, Olga, thanks.
Thank you.
Okay, are there more questions?
Bye.
So I don't see any more questions. So I would say let's thank the speaker again and let's close. Thank you.
Thank you.